maximums and minimums. It says some of the most important applications of differential calculus are optimization problems in which we're required to find the optimal or the best way of doing something. And like some examples of that they give us here are, what's the shape of a can that minimizes manufacturing costs? What's the maximum acceleration of the space shuttle? What's the radius of a contracted windpipe that expels air most rapidly during a cough? At what angle should blood vessels branch to minimize the energy expended by the heart and puts the least pressure on the heart? So all kinds of applications of where we would want to minimize or maximize something, and those are called optimization. So let's look at how we could find maximums and minimums. First off, there are two different types of maximums and minimums we're going to look at. On 223, they talk to us about absolute or global maximums and minimums. So for instance, if you're looking at example number 4 down here, if we're looking for the absolute maximum, it is going to be the absolute highest point on that graph. If you're looking for the absolute minimum, it is going to be the absolute lowest point on that graph. So it's sometimes called absolute or sometimes called global. Maximums and minimums are also referred to as extrema because they're like extremes. So extreme values, the plural of that is extrema. A relative maximum or minimum is also called a local maximum or minimum, and they define those for us over on page 224, and they tell me that a local or a relative maximum or minimum is going to be like if we're talking about a maximum, it's going to be the highest value in its locale or relative to what's around it. So for instance, this point right here is not the absolute highest point on the graph, but it's higher than everything around it. It's the maximum value local to where it is or relative to where it is, so it would be a local maximum. Something else that it's important for us to understand is that an absolute maximum or minimum can occur at an endpoint, but a relative maximum or minimum cannot. So I can look at this point and say, yeah, that's the absolute highest of everything that is on my graph, but I can't say that it's the relative maximum because I don't know what the values up here might be or where this graph might go, if it would go back down or if it would go back up. So I don't know what's in its locale. I don't know what's relative to that point, what's right around it, because I can only see on one side of it. So an absolute maximum or minimum can occur at an endpoint. A relative maximum or minimum cannot. Something else that we want to stress is that the x value in your ordered pair, like, for instance, if we're looking at this point and it were let's choose a different one, negative 110, if that's what that point were, okay? The negative 1 tells me where the maximum or minimum occurs. The y value is the actual maximum or minimum. And so that's important because sometimes they'll say, where do you have relative maximums and minimums? Where do you have absolute maximums and minimums? Other times they'll say, what is the absolute maximum or minimum? So where it is, or how many of a certain item you have to produce to maximize something, or how far away something was when it reached its maximum, those are the x values. But when they say what is the actual maximum or what is the actual minimum, that's our y value. So as we're going through on a lot of these, we'll stress I have a maximum of 27 that occurs at 2. You don't have to write it that way on the test or on the AP exam. We're just trying to stress this is the maximum and this is where it occurs so that we know that we've got it covered. Okay, so for the first example that they give us here, they just give us a graph. And they don't even have these labeled with x values. They have them labeled with letters down here. They've not given me y values at all, so I'm not going to be able to tell what the maximums and minimums are. I'm just going to be able to tell where they are. So they ask me to tell where is the absolute maximum. So where's the absolute highest point on this graph? At D, right. So the absolute highest point is there, and that occurs at D. So I could say I have an absolute maximum at D. Where's the absolute minimum? At A, right. The absolute lowest point is at A, and even though that's an endpoint, Remember that absolute maximums can occur at endpoints. Relative, no, but absolute, yes. All right, how about local maximum? D. Where else? Because you can have more than one. At B, So this is higher than everything around it, and this is higher than everything around it. How about local minimums? C and E, exactly. This is lower than everything around it, and this is lower than everything around it. All right, look at example 2. For example 2, we've got y is equal to x squared. That's the parabola that we know what it looks like. So let's find our absolute maximum. What's the absolute highest value on that graph? So if I come over here and I say, is this point right here higher than everything else on the graph? I don't know. It's hard to tell because I have an arrow right here, so that shows it's going to keep right on going, right? So is that point higher than everything else on the graph? No. And neither is that point or that one, because it's just going to keep going to infinity, right? Okay, well then infinity is my absolute maximum. Well, in order for something to be the absolute maximum, it is the one point where it's higher than everything else. I got to be able to walk up and put my finger on that one point, right? Can you do that with infinity? No, infinity is not even a number, right? It's just a symbol that represents the concept of something getting infinitely larger without bound. So there are times that you're not going to have a maximum or a minimum at all. That's okay. All right, do I have an absolute minimum? Yeah, where is it? At 0, right. And for this one, I can tell that that's a value at 0, 0. If I couldn't tell, once I figured out my x value, I could just plug it in to find my y value, right? All right, how about a local maximum? Do I have any local maximums? No. How about local minimums? 0, 0, right. All right, look at the next one. We've got y is equal to x cubed. So we've got this cubic function here. So what's the absolute maximum? None. How about absolute minimum? None. Local maximum? None. Local minimum? None. So don't think that you have something wrong if you don't get any at all. That's perfectly fine. So if you think about it for your cubic function, it is a constantly increasing function. If we got to this point and it kind of dipped back down and then went back up again, like it switched from increasing to decreasing and then to increasing again, then yeah, I could have maximums and minimums. But the whole thing is continually increasing, so there's not going to be maximums or minimums. All right? Look at example 4. For example 4, we've got f of x is equal to 3x to the 4th minus 16x cubed plus 18x squared. Grab your graphing calculator if you would, please. And let's throw that equation into our calculator. So again, that was 3x to the 4th minus 16x cubed plus 18x squared. So I'm going to start with a zoom 6 and then I can reconfigure from there. But here's our standard. And I definitely am seeing plenty of x's. I even could shave off some of the x's on the sides, and I'm not seeing enough y's. So let's go back to the window, and I'm going to tell it I have plenty of x's, so maybe I'm just going to go -2 to maybe +5. And then for my y values, we needed more of those. So maybe I'll go -50 and +50. That may be extreme, and I could always adjust from there. All right, so that's better. I'm getting a better picture of what I'm working with. All right. They asked me to look at this from -1 to +4. So this is going to be a closed interval. So if I wanted to, I could either use my table feature to figure out that at -1, my y value is 37, and at +4, my y value is 32. Or I could have done second trace, which is my calculate menu, and ask for my values that way, where I could put in my -1 and find out that that value was 37 and repeat that with the +4. Okay, so closed interval going from -137 to +4 32 was the highest value that we had over there, I think. Okay, so looking at that graph, where are you going to have your absolute maximum? It's going to occur at -1, right? And what is your maximum going to be? 37, right? So I'm going to have an absolute maximum of 37 at -1. All right, how about my absolute minimum? Where's that going to occur? At 3, and it's going to be a minimum of what? -27. And of course, when we're working with our graphing calculator, we've done this repeatedly before, but I could get my calculator to verify that by using my maximum or minimum button. So I'm going to verify that minimum that we just did. And because there are several minimums, I mean, I have a minimum here, so I need to give it the region where I want it to look. So that's why it's asking me for boundaries. So I'll give it a left boundary and a right boundary and a guess, and it will verify for me that minimum of 3 -27. So I know we've done that repeatedly before on our calculator, but just reinforcement there that my calculator will tell me the same thing as what we just got. All right, how about relative maximums? Where do I have relative maximums? Relative maximums at 1, 5, right. How about at -137? Do I have a relative maximum there? Why no? It's an endpoint, so relative maximums do not occur at endpoints. So the only one I'm going to have is a maximum of 5 at 1. How about minimums? Yeah, 0 and 3. So I'm going to have a minimum of 0 at 0, and I'm going to have a minimum of -27 at 3. Good. All right, so over on the top of page 225, the extreme value theorem says if you have a continuous function on a closed interval, then your function will have to have an absolute maximum and minimum at some number C and D in that interval from A to B. Go back to these guys that we were working with up here, because remember that like up here I didn't have a maximum and here I didn't have a maximum or a minimum, okay? What that theorem says is that if you're working on a closed interval, you are guaranteed to have an absolute maximum and minimum. Because if we had closed this off, like we had put a closed dot here and a closed dot here, wherever you want to, you just got an absolute maximum, right? Because it can occur at the endpoint. Same story here. If you're looking at this graph and you put an endpoint here and you put an endpoint up here, you just got a maximum and minimum. So if you're on a closed interval, you will always get an absolute maximum or minimum, is what they tell me on the top of 225. Something else that they mention is that you can have multiple places where you have that maximum or minimum. Like, let's say that we had said for y equals x squared, we want the closed interval from -2 to +2. Well, then this is going to be the point -2,4, and this is going to be the point +2,4. So if I say, what is your absolute maximum? Your one value that's higher than all the rest, it's like, wait, I have two of them. Like, I have -2,4 and I have +2,4. How can you have 2 points that are the absolute maximum? What's the maximum, the x value or the y value? The y value. You're only getting one absolute maximum. It's 4. Yes, it's occurring at multiple places, but it's still just one absolute highest value, right? So yes, you can have 5 different places the maximum or minimum occurs, but you will only have one absolute maximum value or one absolute minimum value. Over on page 226, they talk to us about Formos Theorem. Formos Theorem says if your function has a local maximum or minimum value at c, and if the derivative at c exists, then the derivative at c will equal 0. If you have a local maximum or minimum at c, and if the derivative at c exists, then your derivative is equal to 0. What have we used the derivative equal to 0 for before? What did we use it to find? We found the derivative set it equal to 0 to find what? Horizontal tangent lines, right. And horizontal tangent lines, if you came to this graph right here and you drew horizontal tangent lines, you'd get one right here and one right here and one right here. Wouldn't that identify relative maximums and minimums? So that's what that's saying. If you have a local or a relative maximum or minimum at c, and if the derivative exists at c, then your derivative at c will equal to 0. If you set the derivative equal to 0 and solve it, you could find possible places where you would have relative maximums and minimums. Now, the converse of that is not true. They did not just say that if you take the derivative and set it equal to 0, you are guaranteed there's a maximum or minimum there. Because look at this function, f of x is equal to x cubed. If I went through and I took the derivative of x cubed, which is 3x squared, and I set that equal to 0, I get x equals 0. There is not a relative maximum or minimum at 0. Remember, it didn't have any. So the converse of Formos theorem is not true. Just because the derivative equals 0 does not guarantee you that you're going to have a relative maximum or minimum there. You would have to look at the graph to figure it out, or later on we're going to get a test to determine that. But if there's a maximum or minimum value for that function, setting the derivative equal to 0 will give me a way of locating it. Now, setting the derivative equal to 0 is not going to find all of them, because look at the next one. For the next one, if I go through, I've got a relative minimum right here at 0, right? But you and I both know that the derivative does not even exist at 0. Because if you think back to differentiability, when we look at a graph, anywhere you have a corner or a kink, the derivative from the left doesn't equal the derivative from the right, and it's not differentiable, right? So I know that the derivative can't equal 0 there because the derivative doesn't even exist there. So if I had gone through and I had used Formos theorem and I had taken the derivative and set it equal to 0, it wouldn't catch that guy. So that leads us to critical numbers. Critical numbers will give us a way of locating all of the possible relative maximums and minimums. We're going to combine the two ideas that we were just talking about. We're going to figure out where our derivative is equal to 0, because that's like the idea of the horizontal tangent lines. That'll locate the relative maximums and minimums. But we're also going to put that in combination with where the derivative doesn't exist. Because where the derivative doesn't exist, you're going to get a corner or a kink, right? And at a lot of those corners, you would have a relative minimum or a relative maximum. And setting the derivative equal to 0 isn't going to find that because the derivative doesn't even exist there. So if I go through and I find where the derivative equals 0 and I find where the derivative doesn't exist, then we're going to call those critical numbers. Those critical numbers will identify for me where I have possible maximums and minimums. Okay? So if my function was x to the 3/5 times 4 minus x, and they asked me to find all the critical numbers, step number 1, I'm going to take the derivative. Now, we've done that a bazillion times by this point, so I'm just going to give you what the derivative is here, but if you want to see that worked out, they did work that out in the textbook of how they got that derivative. So if I'm looking at my derivative and I want to find the critical numbers, first I need to know where the derivative equals 0. So that's a fraction. Where does a fraction equal 0? Where does a fraction equal 0? Where its numerator equals 0. Right, so let's take its numerator and set it equal to 0. So I'm going to add 8x and I'm going to divide by 12. and then I'll just reduce that. So x equals 3/2 is one of my critical numbers. Then I need to figure out where my derivative doesn't exist, where it's not differentiable. So if this is my derivative, where would this fraction not exist? Where the denominator equals 0, right? So let's take that denominator and set it equal to 0. So I'll divide both sides by 5, and I'll have x to the 2/5, raise that to the 5/2, or take the 5th root of x squared, whichever way you want to think of it, we'll get x equals 0. So those are my two critical numbers for this function. So those are the two places where I might have relative maximums and minimums. So the last thing there on the bottom of 227, it says, if your function has a local maximum or minimum at C, then C will be your critical number. So by finding the critical numbers, we're locating the possible maximums and minimums. No guarantee that it's going to be a maximum or minimum, but it's a possibility. And then I could look at the graph to see what's going on at that point. And again, later on, we'll get a test for that. Okay, so let's sum up what we know so far. All local maximums and minimums are critical numbers, but not all critical numbers are local maximums and minimums. And that goes back to our example of like y is equal to x cubed. We found a derivative equal to 0 at 0. That was a critical number, but I didn't have a maximum or minimum there. Endpoints can be absolute maximums and minimums, but they cannot be local maximums and minimums. Endpoints can be absolute, but they cannot be local. And then every continuous function on a closed interval has an absolute maximum or minimum. Open intervals may or may not. So, for instance, this one, if it's on an open interval where it's going to keep going infinitely, it would have an absolute maximum but not an absolute minimum. If instead I closed that off and gave it endpoints, then it would have an absolute maximum and an absolute minimum. So, how then can I find my absolute maximums and minimums if I have a closed interval? Okay, we've seen that absolute maximums and minimums can occur at local maximums and minimums, right? Or they can occur at endpoints. So we want to go through and find all of the local maximums and minimums and the endpoints, and then just compare their y values and see which one is the absolute highest and which one is the absolute lowest. So step by step, number 1, find all your critical numbers. And then number 2, find the values of your endpoints, and then just compare them in step number 3. The largest y value is going to be your maximum, and the smallest y value is going to be your minimum. So example number 8. It says you've got the function x cubed minus 3x squared plus 1 on this closed interval negative 1/2 to 4. So I know it's continuous because it's a polynomial function, and all polynomials are continuous everywhere, and it's on a closed interval. So I am guaranteed it's going to have an absolute maximum and minimum. All right, so step number 1, let's go through and find the critical numbers. So to find our critical numbers, we'll set our derivative equal to 0. So what's the derivative? Yeah, 3x squared minus 6x. So if I set that equal to 0, I'm going to take out the greatest common factor and then set each of my factors equal to 0. So I'll get x equals 0 and x equals 2. Now, when I'm going to compare in my very last step, remember I'm comparing the y values because the y values are the maximum or the minimum. I'm comparing the y values to see which is the highest or which is the lowest. So if that's the case, then I need to go ahead and find the y values for these. If I know x, how do I find y? Plug it back in. Do I plug it back into the original or do I plug it into the derivative? The original, right, because it's a maximum or minimum of the original function, right? So if I take 0 and I plug it back in up here, I'm going to get 0 cubed minus 3 times 0 squared plus 1, so I'd get 1. And if I take 2 and plug it back in, 2 cubed minus 3 times 2 squared plus 1, then that's going to give me negative 1. So I have 0, 1, and I have 2, negative 3 so far. Plugged in 0, got 1, plugged in 2, got negative 3. All right, now step number 2, I need to check my endpoints. So same story. I'm going to take negative 1/2 and plug it into the function, and I'm going to take positive 4 and plug it into the function to get the y values. So absolute maximums and minimums could occur at the relatives, so we got those covered down here, or it could occur at the endpoints, so we've got those covered right here. So now we're just going to look and see for the absolute minimum, out of all of those, what was the lowest y value? -3. So I have a minimum of -3, and that was at 2. All right, what was the highest of all of those y values? 17. So I have a maximum of 17, and it occurred at 4. All right, let's look at another one of those since we love trig stuff so much. Let's look at a trig one. Example 9, it says, find the absolute maximum and minimum for x minus 2 sine x on the interval from 0 to 2 pi. All right, so I have a trig function. I know that trig functions are continuous within their domain, and the domain for the sine curve is all real numbers. I put that in combination with a polynomial function. Polynomials are continuous everywhere. So remember, when I add two continuous functions, then it's going, that combined function is going to be continuous in that same interval. So we can say, okay, this is going to be continuous from 0 to 2 pi, and I do have a closed interval, so therefore I know that I'm going to have an absolute maximum and an absolute minimum. So step number 1, let's take our derivative and set it equal to 0. So derivative of x is 1, and derivative of 2 sine is 2 cosine. So how am I going to get x by itself? All right, subtract 1 and divide by -2. So I'll end up with cosine is 1/2. So I need a reference angle. Where is cosine equal to 1/2? Pi over 3, yes. And cosine is positive in the first quadrant, and where else? Fourth. So I'm going to have to give the first quadrant pi over 3, which is pi over 3, and the fourth quadrant pi over 3, which is 5 pi over 3. Alright, so now I have my x values. I got to plug them back in to find my y values, right? So let's start with pi over 3. If I take pi over 3 and I plug it back into the original function, that would be pi over 3 minus 2 sine pi over 3. So that's what we've got right here, pi over 3 minus 2 sine pi over 3. So what's the sine at pi over 3? Square root of 3 over 2, right. So I'm going to do square root of 3 over 2 times 2, which would just give me square root of 3. So I'll get pi over 3 minus square root of 3. All right, then let's do the same thing with 5 pi over 3. Let's take 5 pi over 3 and plug it into the function. So that would be 5 pi over 3 minus 2 sine 5 pi over 3. 5 pi over 3 minus 2 sine 5 pi over 3. Sine at 5 pi over 3 is still square root of 3 over 2, but it's negative, right? So if I do -2 times negative square root of 3 over 2, that's just going to give me a positive square root of 3. So these are my ordered pairs. And I always want to give exact answers, so I don't want to give the decimal approximation unless I'm told to, but I don't have a clue how to compare those. I need actual numbers for those. So I am going to throw that in and get an actual decimal so that I have something to compare to figure out what's the highest y value and what's the lowest y value. All right, so that was step number 1. Step number 2, we got to do the same thing with our endpoints, right? We have to take the endpoints 0 and 2 pi and plug those into our function and find y values. So if I take 0 and I plug it into my function, that'd be 0 minus 2 sine 0. What's the sine at 0? 0, right. So I'm going to get 0 minus 2 times 0, so that would just give me 0. All right, similarly, I'll plug in 2 pi. So that would be 2 pi minus 2 sine 2 pi. Sine 2 pi is 0, so that would be 2 pi minus 0, so just 2 pi or 6.28. Alright, so now I have all the y values that I could compare. So I've got -0.68, 6.97, 0, and 6.28. Which of those is the highest? Yeah, the 6.97. So that came from the 5 pi over 3 plus the square root of 3. That's this guy right here. So I want to go back to giving it in its exact value. So I could say I have a maximum of the y value that's occurring at the x value. So maximum of the y value occurring at the x value. How about the minimum? What was the absolute minimum? Yeah, it was the negative 0.68, and that was coming from this first point. So again, I'll go back to those exact values and say I have a minimum of the y value occurring at the x value. So if I look at that one, I didn't even need the endpoints. The absolute maximum and minimum both occurred at the relative extrema, but I don't know that if I don't check them. Because in the previous example, it was one relative extrema and one endpoint, right? So it can occur at either. All right, so here is our homework for section 4.1 on pages 230 to 231.